Sushruta for NEET is now available on the Google Play Store. Try it out for free.
So today I will have a shorter class, and the aim of this class is to wind down all the material that we have discussed so far with electrostatics. If we may look at the ideas in electrostatics, we first began by looking at the idea of uh, uh, firstly charge. We started with charge, then we went to Coulomb's law, right? Charge as an idea um, is something that uh, you know um, was well understood because of the Greeks, etc. Right? And now we then introduce Coulomb's law, which says that when you have a positive, and basically there is positive charge and negative charge, and the lowest charge you can have is the charge of the electron is 1.6 × 10⁻19 coulombs, right? And we said that like charges repel, unlike charges attract, and we then uh, defined the ideas around uh, Coulomb's law, right? And where 1/4πε0 Q1 Q2 by R square is the force. Then we introduce this idea of the electric field, which is a vector, which is the force that would be experienced by a unit charge at a particular point in space as a result of one or more charges, right? And so we said that it is the it uses the superposition principle. Therefore, you just sum the vectors, right, at any particular point, right? Due to the various charges, the sum of those vectors produces the electric field, right? Then we introduced this concept of the electrostatic potential, which was related to the idea of work. Electrostatic potential is the work to bring a charge from infinity to that point in an electric field, right? Now, force is the force felt at a particular point. Work is the work done to move it from infinity to that particular point, right? So, and it is a scalar. It is easier to calculate the electric field. Okay. Now, what is the potential at a particular point? Potential at a particular point is Q by 4πε0 R, right? So, equipotential surfaces with electric field perpendicular, right? So, now we then introduce the relationship between the potential and the electric field, right? How just like work and force are related, right? F dot dx will give you the work, right? We also said that and the inverse of it is that the gradient of the electric field, right? And when we say gradient, it is a derivative with respect to r or distance, right? So gradient is always like, if you look at a slope, right? We call it a gradient, right? So when it slopes up, it's a gradient. It's a amount of increase in the slope with distance, right? So similarly, dV by dr gave you the electric field with the direction being normal to the to all the equipotential surfaces, right? So if you had an equipotential surface normal to that equipotential surface, you had the electric field. So if you had all these points which were part of the equipotential surface, this would be normal to that, right? So that's how we define potential, right? And then we said you have these equipotential surfaces, and then you have the gradient, right? Gradient is how fast something rises up, and so that's how you have the gradient. Okay, so now work done in moving a unit charge from A to B, right, is E dot dl. And so and dv by dx is E, right? So dv by dx is E, and so that is was the relationship between electric field and potential, right? And so if you then wrote it in this form, let's say you have a point charge and you have a point, then q by 4 pi epsilon naught r, right? Then you can differentiate dou negative dou v by dou x, etc., right? Then you ended up with the equation of the electric field, right? So what is this dou v by dou x? Dou v by dou x is when you take the derivative with respect to just x, keeping y and z constant, right? Or keeping everything else constant just with respect to x. So if it is a function of x, right? So in this case, q by 4 pi epsilon r is root of x square plus y square plus z square. That is the position vector, right? So now, so because of that, when you take the derivative, you end up with minus q by 4 pi epsilon naught 1 by x square plus y square plus z square to the power of 3 by 2 times half times 2x, right? So how do you end up with that? So this is for this one itself, right? So this itself is a function x to the power of minus half, right? X to the power of n, the derivative of something is n x to the power of n minus 1, right? So so in this case, n is half, negative half, right? So negative half is this is n x to the power of n minus 1 will become x square plus y square plus z square to the power of negative 3 by 2, right? And then if when you differentiate the part inside, you end up with this term 2x, right? So n x to the power of n minus 1, n was negative half, right? So one because it is 1 by x square plus y square plus z square, it is therefore the power is when you take that to the numerator, it becomes x square plus y square plus z square to the power of minus half. So that when you say n x to the power of n minus 1, it is minus half x square plus y square plus z square to the power of minus 3 by 2, right? Therefore, you end up with this term, right? And then so the negative dou v by dou x I plus negative dou v by dou x dou v by dou y j negative dou v by dou y k, right? And therefore you end up with the three vectors, right? So now inside the conductor, the electric field is 0, right? And therefore conductors with a cavity, right? Therefore, if you had a cavity within the conductor, there is no charge inside that, and therefore, if there is no charge, right, then you correspondingly end up with no field in. There's no enclosed charge, then the corresponding line Gaussian surface will produce no field, right? So we then dealt with that. Then we looked at how to apply electric field to points inside and outside, right? So let's take a look at this example. Consider a spherical conductor, right, with a spherical cavity centered in the conductor. Okay, so now you have a conductor. So he is dealing with these cavities inside a conductor, right? So what happens in a conductor? The charge will flow to the surfaces. A charge of negative q is placed at the center of the cavity, right? Calculate the surface charge density on the inner and outer surfaces. Calculate the electric field everywhere, right? So now what happens, right? So when you have a potential at a point outside a conductor with a charge, right? So if you had a particular charge, you draw a Gaussian surface around it, and the resultant will let you calculate. It will then let you calculate E dot dA. Closed surface integral of E dot dA is Q by epsilon, right? So using that, you can calculate the electric field, and from the electric field, you can then calculate the potential. Okay, that is one way to do it. Okay, the other way is just use Q by 4 pi epsilon naught R, right? And then go from there. Okay. So and most often, right, you calculate the electric field, and you then say that dV by dx is equal to A is equal to E, and then if you have E, then you have E dot dx will give you V. Okay. So then we introduce the idea of the capacitor, right? The capacitor is a particularly different kind of animal, in that it is consists of two plates, right? There is and when you apply a battery to a capacitor, what happens is, when you first switch it on, charge builds up on the two plates, right? Then it reaches the equilibrium. So normally, when you have a capacitor and you just switch on the capacitor, when you switch on the full circuit, right, what will happen is there will be a spike. During that time of the spike, the charges are building up. Okay, so then everything stops. That is, it goes up and then it kind of stops. Okay, so that happens, and then you have no current after that. And that's how a capacitor behaves in the presence of a battery, right? There is in steady state, there is no current. There is a spike, and then there is no current. So now, when there is the spike, what happens? There is the charge buildup, right? So during that time of the charge buildup, there is a certain type of what happens to the medium inside the capacitor. We already introduced this idea of a dielectric, right? Dielectrics, in the they go through a process called polarization. Okay? Inside the capacitor, one plate is charged positive. Outside one plate is charged positive. And another plate is charged negative, right? Now, inside the capacitor, that is, whatever medium is there, the elements in that medium, which normally are don't have any charge, right? Those elements will then experience a certain amount of what we call polarization. That is, some of the charge will go towards towards the negative plate. So, that is, the positive charge will go towards the negative plate. Negative charge will go towards the positive plate. This process of separation of charges inside the dielectric is said to lead to polarization. And and in fact, according to Ampere, right, he therefore introduced a change in epsilon naught E, right? He introduced another term called P. Okay, he introduced what is called polarization to change the electric field, right? So he introduced this term D is equal to epsilon naught E plus P. Okay, and so we will be looking today a little bit at that, okay, at this what is called polarization and the resultant displacement current. Okay, so this is a common thing that occurs in capacitors. So when you first introduce the charge, one side will get the positive charge, one plate will get the positive charge, the other plate will get a negative charge, and there will be a electric field inside the in between the two plates, right? And the value of the electric field is V is equal to E times D, right? Q, as you know, is equal to CV, right? And C is equal to epsilon naught A by D, right? So based on that, if you apply a voltage V and then you can say that the corresponding charge is Q is equal to C times V, right? The charge is proportional to the voltage. Q is proportional to the voltage, and therefore C times V, right? And C is epsilon naught A by D. So that defines this whole, that defines your capacitance, and correspondingly, epsilon naught A by D, epsilon naught is 8.85 to the power minus 12. And if you had a dielectric present in between the capacitors, that will introduce a dielectric constant to the equation K times or epsilon R times epsilon naught A by D, right? So you introduce K times epsilon naught A by D, right? When you introduce the dielectric, so it becomes K times C if you introduce the dielectric, and K could be some constant number, right? Or known as the dielectric constant. So K epsilon naught A by D will become the new capacitance, right? So in the parallel plate capacitor, right? And so using that, you can then change your equation to Q is equal to CK times V, right? So the difference between a capacitor with a vacuum and a capacitor with a dielectric in between, right? Um, or some completely insulated material versus a dielectric, right? So that is the basis of Q is equal to CV, right? And so that introduced this idea of the parallel plate capacitor, right? So now let's take a quick look at a couple of problems, right? Parallel plate capacitor with area of plates 1 meter square each are at a separation of 0.1, right? So D is 0.1, A is 1 meter square. So epsilon naught, 8.85 10 to the power minus 12, right? That is taken to be the magnitude of the charge, right? If the electric field is 100 newtons per coulomb, right? So epsilon naught A by D, right? So if the electric field is so much, the magnitude of the charge on each plate, Q is equal to C times V. C you already calculated, epsilon naught A by D, right? Where epsilon naught is 8.85 10 to the power minus 12. A is 1 meter square, D is 0.1. So using that, you can calculate C, right? Now, if you are given the electric field, from that you can calculate the V, right? What is V? V is dV by dx is V, right? V is, so E is given to be 100. So 100 times 0.1 will give you the corresponding V, right? So we calculated the C, then we calculated the V, right? So 100 times 0.1, and then so from that, if you calculate the net epsilon naught A by D, right, it will give you the resultant Q, right? So from the E, we calculated the V. From the dimensions of the capacitor, we calculated the C, and then from C times V got us Q. So that is the magnitude of the charge on each plate, right? Now, if you had a cylindrical capacitor, in the case of the cylindrical capacitor, it is one, inside there is one, one conductor. Outside there is a bigger conductor. In between, you can put a dielectric between the inner and the outer, or you can put some air, okay, air filled capacitor. So then if E is equal to, and then you can apply, build a Gaussian surface, right? And then if you build a Gaussian surface at a distance r, then you have 2 pi r times L. You build a cylindrical Gaussian surface. 2 pi r times L, right? And then at each point you have a corresponding, for the um, um, for this side of it, the flat side, the thing with the E dot dA will go to 0, right? Because the E will always be like this, right? And the A will in those places will be like that, right? So it will only work in the cylindrical side. So 2 pi r L times E. It's only there that the dA and the E will be in the same direction, right? So 2 pi r L times E will give you the charge enclosed. The charge enclosed is a lambda per unit length. So if there is a length of L, right? So lambda times L will give you the total charge, right? Therefore, you will have lambda times L Q by epsilon, right? So when you apply that, you find lambda by 2 pi epsilon naught R, right? So now E dot dr, right? E dot dr will give you the V, right? dV by dx, dV by dr is E dot dr will give you V. So now when you integrate, you will have E dot dr, you end up with ln B by A, lambda by 2 pi epsilon naught ln B by A, right? Therefore, that produces your corresponding V, right? And then you have Q is equal to CV, right? Q is lambda times L, and therefore, because Q is lambda times L, you can replace lambda with Q by L, right? Therefore, you end up with Q by 2 pi epsilon naught L ln of B by A, okay? And therefore Q is equal to CV. So that is the resultant capacitance 2 pi epsilon naught L divided by ln B by A, right? So the so in these kinds of equations, you relate Q is equal to some constant times B, right? That constant is the capacitance. Okay, and therefore, using that, we found the capacitance to be 2 pi epsilon naught L by ln B by A, right? So that is the, and if you wanted to calculate the capacitance per unit length, it is C by L. Okay, so if you had an example, you can then calculate, if you gave A and B, you can then calculate the corresponding capacitance, right? So now, if you have a spherical capacitor with two radii, same principle applies. Instead of having a cylindrical Gaussian surface, you now have a spherical Gaussian surface. What is the area of a sphere? You know, the volume of a sphere is 4 by 3 pi r cubed, right? Now the area of a spherical surface is 4 pi r square. So 4 pi r square times E, right? E dot dA 4 pi r square times E will give you Q by epsilon naught, right? And therefore you have the effective E is equal to Q by 4 pi epsilon naught R square times R. Then therefore, when you do the integration, you will end up with Q by 4 pi epsilon naught times 1 by R. Therefore, then you can get the corresponding V, and everything that remains in the relationship with V is equal to some constant, Q times some constant, Q is equal to CV. Therefore, 4 pi epsilon naught RA RB by RB minus RA will therefore be the capacitance, right? Everything else in the Q is equal to CV form will give you capacitance. Or even you reduce it to the form Q by V, right? If you had this equation, reduce it to the form Q by V, everything on the left hand side will give you C. All right. Now, if one of the, if you look at, if you made RB, right? RB is the radius of the outer sphere, it is very, very large, then you correspondingly you just end up with the inner sphere, 4 pi epsilon naught RA. Okay. and using that you can then calculate it. Okay, so the simple idea with evaluating the capacitance of all these differently shaped surfaces: build a Gaussian surface around the particular charge, around the particular sphere, around the particular cylinder, and then you reduce it to the form Q is equal to CV, and then you can evaluate the C. Okay, so based on that, he calculated the capacitance of the Earth to be 4 pi epsilon naught R. R is the radius of the Earth. Okay. Now, we then introduced the concept of capacitors connected in series and parallel, right? If you had three capacitors in series, we said that the sum of the voltages will be the voltage of the source applied at the side, right? And so the sum of the voltages across C1, C2, and C3 will be V1 plus V2 plus V3 will equal V, right? And as a result, the charge on each of the across each of the capacitors will be a constant when the capacitors are connected in series like this, right? The charges will be a constant. So Q is equal to CV. V is equal to V1 plus V2 plus V3, and each of the V's will equal Q by C1 plus Q by C2 plus Q by C3 will equal the net Q. Let's say we wanted to replace this with one capacitor. So the net Q will be the same, right? So the V is equal to V1 plus V2 plus V3, right? So Q by C1 plus Q by C2 plus Q by C3 will equal Q by the net C. So 1 by C, if you wanted to replace C1 plus C2 plus C3 with a single capacitor C, 1 by C will equal 1 by C1 plus 1 by C2 plus 1 by C3 for this set. So for a series equation, 1 by C1 plus 1 by C2 plus 1 by C3 will equal 1 by C, where C is the equivalent of, if you replace C1 plus C2 plus C3 with one big capacitor, what will be its capacitance? Its capacitance will be 1 by C equal to, such that 1 by C equals 1 by C1 plus 1 by C2 plus 1 by C3 for series, right? For parallel, C1 plus C2 plus C3 will equal C. Okay. So, and if you had some series parallel combination, you can then evaluate the corresponding capacitance. Okay. So, that is how you do it. So, this is capacitance in series. This is capacitances in parallel. Okay. So, and then if you have some combination, you just do the corresponding arithmetic. Okay. So, let's look at this example. This capacitance has C1, this capacitance has C2 and C3. So now if we replace, so in these cases, you first replace these two, C2 plus C3, either the capacitance of this is merely C2 plus C3, that is merely 25. So this is 25, and then you replace C2 and C3 with another 25. So 1 by 25 plus 1 by 25 equals 1 by C, right? And so 1 by 25 plus 1 by 25 is 2 by 25. So so the net C will equal 25 by 2, right? So what is 25 by 2? It is 12.5, right? So that's the simple answer there. So you should end up with 12.5. Okay. So and if you applied a voltage across of 10 volts, the corresponding current will be Q is equal to the corresponding charge will be Q is equal to CV, right? C is 12.5. 12.5 times 10 will give you 125 microcoulombs. Then you can evaluate both the voltage across each of the capacitors as well as the charges, right? The charge across all of them will be the same, right? The charge across C1 will equal this value, 125 microcoulombs. That's the charge across this one. The charge across these two will sum to the same 125. Okay, And so that's how you can evaluate the values. Okay. So now we then looked at this example. See, if you had a parallel combination of two air-filled parallel plate capacitors C and NC connected to a battery, the capacitors are fully charged, the battery is removed. After that, a dielectric material is of dielectric constant K is placed between the two plates of the first capacitor, right? So you have two capacitors, C and NC connected, right? Parallel combination. So in the parallel combination, what is the net capacitance? N plus 1 times C, right? So because the parallel combination N plus 1 times C, so now the capacitor fully charged, the battery is removed, and after that, direct K placed between the capacitor of the first capacitor. So now you have K introduced into the first capacitor, right? So the net C now is K plus N times C, right? So now what happens when you introduce the new capacitance? The charge reconfigures itself, right? Q is initially was CV N plus 1 times C times V. So now you introduce the new capacitance N plus K times C. Therefore, N plus 1 times Q, right? V times N plus 1 times C divided by N plus Q by new V will be Q by C, right? And the Q new, we already calculated the Q, and the new C is N plus K times C. So V times N plus 1 divided by N plus K. Okay, so that's how you solve these problems. And so remember to use these considerations and go about solving a problem. So what is the work done in the context of a capacitor, or the charge, right, or the charge energy? The basically capacitors store energy. So if you apply a field, it will then store in the form of the positive and the negative charges being kept together, right? That is a store of potential energy. Okay, and so when you remove the battery and then you connect a full circuit, it will then discharge. Right, the capacitor will itself act like a battery and then discharge. Okay, so now the stored energy is what is the value of the stored energy? Half CV squared, or Q square by 2C, right? So VdQ will give you the stored energy, right? Q times V is actually the energy, right? And therefore Q dQ, V dQ will give you the stored energy. So work done is therefore the integral of V dQ. So V is Q by C, and therefore you have Q square by 2C, and you integrate that, right? So V dQ will give you the work, and when you integrate that 0 to Q, you end up with Q square by 2C. So half CV square is the energy in a parallel plate capacitor, and you can evaluate that. Okay. So now correspondingly, you can do the same with these other terms as well. Okay. Therefore, you can look at VdQ. You can do for all these. For this as well. The capacitance is so much. Therefore, otherwise you can do Q square by 2C. Therefore, you end up with corresponding equation. All right. Stored potential energy you can then evaluate. All right. So then we looked at a few of these problems. The figure 1 shows the line of constant potential in a region in which the electric field is present. Values of the potential are written in brackets. Of the 3 points, the magnitude of the electric field is greatest at which point, right? These are equipotential lines, 10, 20, 30, 40, 50, right? So remember that the field is the gradient of the potential, dV by dx, right? So now, where does it change the fastest? Where is the gradient the highest? It is between 10 and 20, right? So, so at point B, right, the gradient is the most. So between the two lines 10 and 20, it's going up the fastest with respect to distance. So where the potential goes up the fastest with respect to distance, that's where you have the maximum electric field, because it's dV by dx. Trying to see if you understood that. Okay. So now the other questions are also similar, right? Two small balls have equal charges and are suspended by insulating thread from a hook to a stand. Whole system is taking a satellite to space, right? So where there's no gravity. So now the angle between the strings will be what? It will just stretch out because the like charges repel. So it will just stretch out and go further from each other, right? Till the string holds it together, right? There's only two forces. There's the string and then there's the balls, right? So they will make a 180-degree angle between each other, go to the furthest from each other, and the tension in each string will be the charge of repulsion, right? Q squared, 1 by 4 pi epsilon naught Q squared by R squared. And R square is what? 2L the whole square, right? 1 by 4 pi epsilon naught Q square by 2L the whole square will be the tension, because that is the force between the charges, the direct application of Coulomb's law. Two parallel plate capacitors, 2C and 2C are connected parallel. So the net is exactly the same as this one. So the net charge as this question. Okay. So the net charge is C plus 2C is 3C. Battery is connected. Therefore, what is the charge? Charge is Q is equal to CV. So 3C times V. Then the region between the plates of the capacitor C is filled with a dielectric, so that will become Kc. So the net will become K plus 2C. Potential now becomes, correspondingly the Q divided by the new C, right? New C is K plus 2 times C, right? So the Q was V times 3C, right? So Q is equal to CV and C was 3C, right? 3C times V. In this case, K plus 2, right? So correspondingly, you can then calculate the potential difference, new potential difference. Okay. So a point charge moves from point P to S along the path, right? And the coordinates of it are P is A, B, 0, right? Then this is 2A, 0, 0, A minus B, 0, and 0, 0, 0, right? So the work done in the above field is given by the expression. Well, it only depends on the E dot A, right? So Q times E dot right, work is Q times force times distance, right? Now because the field is in this direction, you only worry about the X component, and the X component we know is just A, right, for the point P. So A times right, A times EQ, right? EQ is the force, F times D, right? F times A, right? So EQ times A will give you the work done. All right. So now we will to wind this down, we are going to introduce some of these additional terms, right? The first is additional ideas. The first is what happens in the context of when there is a dielectric, right? Dielectrics in the context of the charged capacitor, right? The dielectric itself will behave like a dipole. initially the dielectric is not charged, but what it will do is it charges inside the dielectric. You think of it as some kind of fluid, right? Inside that fluid, the charges will separate. Okay, therefore the positive charge will go to the negative charge side of the capacitor, and the negative charges will go to the positive side of the capacitor. Okay, and as a result, you can say that during that initial phase, when you first switch on the battery to a capacitor, even though it's a DC battery, and eventually no current flows, during that single phase, there is a flow, there is a corresponding polarization that happens, and therefore you can say that there is a current flowing. Okay, and that's what Ampere said. That is called the displacement current. Okay, now the dipole per unit volume is epsilon naught x times E, right? Where x is said to be the electric susceptibility of the particular material, right? Epsilon naught x times E will give you what is called the polarization. Okay, and the dipole moment, as all of you know, is uh, um, defined to be q times 2a, right? Where 2a is the distance between the positive and negative charge. So in this case, if q is the charge, you can then write the corresponding dipole moment as p times a times l, based on the polarization. Hmm. So if the polarization is p, epsilon naught psi times e, right? The dipole moment is p times a times l, where a times l is the volume. So polarization is the corresponds to charge per unit volume in some ways. Okay, and therefore you end up P times A times L as the dipole moment or charge per unit area, right? And therefore P times A times L will give you the dipole moment for the dielectric. Okay, so so QL will equal P times A times L, or Q is equal to P times A. So the polarization they gave you, it is a charge per unit area. Okay, so how much charge gets, so then you have the bound surface charge density, and the bound surface charge density is sigma B is equal to Q by A is equal to P, right? For bound surface charge density. Okay. So now, if you have capacitor with a dielectric, you can have epsilon naught A by D, right? And therefore, from that, you can then calculate the sigma. Right? P is equal to epsilon naught psi E. Okay, and from that you get sigma. Okay, so and the dielectric constant is 1 plus psi. Okay, so this is how you deal with dielectrics. You have polarization that happens inside the dielectric, and which then leads to a charge density inside the dielectric. And then you can, in order to calculate that, let's say you build a small Gaussian surface there, and then you say, okay, now across this Gaussian surface there is no net charge, therefore it doesn't have a particular E, right? And so that's one way to calculate the corresponding electric field, right? So different materials have different dielectric constants. Glass has almost 5, paper has 3.5, porcelain has 6.5, and then you have ceramics which have 130, and strontium titanate has 310, water has 80. So different dielectrics can be used. Over time, I think copper solutions or other solutions were used, but more and more people have gone away from using fluids in capacitors and replace them with because fluids can evaporate. Replace them with solids. Okay. And so these are Here's another example that they've looked at. They give you the area, and then they give you the distance, and from that they then calculate the corresponding K, right? So if you had a particular material with a particular K, right, you just multiply epsilon naught with K times epsilon naught to give you the dielectrics epsilon. Okay. Um, so that's with respect to dielectrics. Okay, so parallel plate capacitor with air between the plates has a capacitance 9 picofarads, right? The separation between its plates is D. Space between the plates is now filled with two dielectrics. One of the dielectrics has dielectric constant K1 and thickness D1, D by 3. Another one has a dielectric constant K2 of 6 and distance 2D by 3. Capacitance of the capacitor is now, right? So now this is when you fill it with two materials in series, you can think of it as now creating two capacitors. See, the initial capacitance is 9, right? Therefore, if you said that the original D by 3 part, it is going to have a capacitance of 3 picofarads. Now, when you increase its K by 3, it is going to become 3 times that. Therefore, it will be 9 picofarads. The second one is going to have a capacitance, its thickness is 2D by 3, right? So it had 6 picofarad. Then you increased it the sixfold, it will become 36 picofarads, right? So you had 9 and 36 in series. So 1 by 9 plus 1 by 36 equals 1 by C, right? So 1 by 9 plus 1 by 36, when you evaluate that, you will get a corresponding result, right? 1 by 9 plus 1 by 36, right? So, and that's what is being evaluated here. Okay. 1 by 9 plus 1 by 36 is going to give you 36 by 5, right? And correspondingly, you will get the value of the capacitors. Okay. If you did the capacitances in parallel, right? Right. But so that's what you should be doing actually here. Okay, should be evaluating the capacitors in series. You had the capacitors in series. You had to do C1 C2 by C1 plus C2. Okay. So now three types of current. So far we have discussed there are actually three types of current. Okay. Conduction current is when the electrons actually flow, right? You had a metal wire, you have conduction current that happens, and the electrons actually flow from the positive side to the negative side, right? The second type of current is what is called displacement current, which happens just when you switch on a capacitor. Okay, then the polarization inside the dielectric, right? There is no actual flow of electrons through the capacitor, but there is a brief moment when there is a separation of charge inside the dielectric. Therefore, there is at that moment what you call displacement current, and therefore this current it also behaves like a current when you just switch on the circuit, right, which has a capacitor. Then we say that there is a displacement current. Therefore, the displacement field, right, is also called epsilon naught E plus T. Okay, so this was introduced by Ampere, take into account the displacement current. So D is equal to epsilon naught E plus T. So he changed Gauss's law slightly, right, to introduce polarization. Okay, so you have conduction current, which is what we've all know as normally as current. Then you have this displacement current, which is a term which is caused by polarization. And then eventually we will also introduce this other term called drift current, right? Drift current or diffusion current is what you see in semiconductors. Okay? When we deal with semiconductors, we'll take a look at that. Okay? So epsilon naught E plus P, you calculate. So and instead of doing E dot dA, you do D dot dA when you calculate the when you apply Gauss law to material inside a dielectric. Okay, so that is how you do epsilon naught E plus P, as is the net D. D is equal to epsilon E plus P, and then using that you then calculate D dot dA. Okay, and so you then apply. You can calculate the corresponding D dot dA is equal to Q by, is just Q, right? Because epsilon is included in D, right? Epsilon naught E, right? D is equal to epsilon naught E plus P, right? So in closed integral of D dot dA is equal to Q enclosed. There's no divided by epsilon there. Okay? So closed integral of D dot dA is equal to Q enclosed. Okay, and so in the context, in the presence of a dielectric, you have the corresponding Gauss law with displacement current. Okay, and so with that, I'm going to wind down the material for capacitance. Next week onwards, I will move on to regular current with resistance. We'll start with Ohm's law, and then we will go from there on to the follow-on topics in electricity, and then we will go on to AC circuits. First, we'll start with DC circuits, and we'll go to AC circuits, and we will go from there. All right.